Let me grab my phone so I can see problems. Sweet. All right. So what we're going to do today, thank you all for hanging out with me one last time, is work on a section that we just haven't really touched on a whole lot of. I kind of jumped around a little bit, like we did a lot of 4.4 kind of stuff as a mentality, and we're kind of working our way around through that. Hold on, pause for a second. I've got class, so let's take that. We're shooting here. Okay, sorry. All right, so let's do some 4.3 stuff. Okay, and hopefully what today does is kind of wrap things up in a way where you're feeling really good about what we can do with all these ratios. Understand some things about, and I'm going to give this section a title here in a minute, and kind of put things together in a way where once we get back in January, we can really take off with this because we know this stuff really well. So let's do some stuff and hopefully it clicks really, really, really well for you. Again, I put a link on today's announcement for the Apple Awards. So if you're feeling like you have somebody in mind to nominate, feel free to do that. Okay, so here we go. What I want to do in this section is I really want to focus on the first quadrant space only. Okay, I want to focus on quadrant one. Okay, it'll just allow me to stay positive with everything, right? X is positive and Y is positive in the first quadrant, so everything from there is positive, cosine and sine and all the other ones, right? Because if I can do that, then I'm really just worried about like one angle at a time, rather than stuff like yesterday where we had like inverse sine of 1/2. Well, okay, there were like 2 spots that I could do that, right? Things like that. So let's worry only about first quadrant space. So between like angles between 0 and 90 degrees, okay? And the kinds of questions that we could be asked in stuff like this. So I'm just going to call this one number 1. Uh-oh, I hear bloops. What's up? Oh, you're good. No worries, Peyton. Thank you, thank you. Okay, so what we're going to do here, you didn't miss much. I'm going to ask you a question, but I'm going to write it just a little bit differently, right? And I'd love to hear from you, right, one last time, because I won't see you very much after this. Imagine that the question that they asked was cosine of theta equals 1/2. Imagine they wrote that question. So for the first time now, we're actually seeing a whole equation, not just an expression, right? And of course, I mean, the only missing piece here is just theta, right? And so if we're given a trig, regular trig expression, no inverse here yet, regular trig, the thing that we're going to be asked for, if it's an equation, is what's the angle, right? What angle is going to make that happen? And so think just first quadrant only. Unmute yourself if you've got an answer. If cosine of theta is equal to 1/2, what is that angle?
45.
60 degrees.
60 degrees, and let's stick with radians. What's the radian version of that?
Pi over 3.
Nice, good. Right? And we can do that really nicely because we recognize that 1/2 as an amazing unit circle spot. And whether the angle that I'm drawing is in a triangle that fits in the unit circle or is humongous or is a whole lot smaller, doesn't matter. The angle itself is still going to be pi over 3 when I draw that triangle to make that happen, right? And so that's pretty nice, right? If they give me unit circle spots, so I'm going to do another one. Sine of theta number 2, let's call it. Sine of theta is √2 over 2. What angle is going to give us a sine in the first quadrant, a y value, right, of √2 over 2? What is that answer?
Pi over 4.
There's that 45 degrees, right? Perfect, pi over 4. Now, but what's happening in between here algebraically? Now, I don't think we necessarily have to show this work, but I want you to see how this is all happening. In order for me to kind of break theta out from inside that trig function, right? Sine of theta is a function of theta that gives us the y value of the spot on the unit circle, blah, blah, blah. I should be able to solve for it algebraically by using trig, right? And like treat it like it is, right? Treat it like an equation. I just want to do some things to one side and then, of course, the other to kind of undo what's happening to theta. And if this was like algebra 1, we'd solve equations like 3x equals 12, right? And if 3x equals 12, then the thing that's connected to my variable is a number by multiplication, so I just want to do the opposite, right? We'll divide by 3. Or if it was like x plus 8 equals 19, okay, I'll subtract 8 on both sides. Well, it's not that this is sine times theta, right? It's sine of theta. I have a function, sine. I want to do the opposite of taking the sine of something. What do you think? What's the opposite of sine?
The inverse of sine?
Nice, right? Every operation has its inverse. And so if I were to take the inverse sine of the left-hand side, which is sine of theta, the sine and the inverse sine cancel each other out, right? And all I would be left with in that case is just theta, right? And whatever I do to the left, though, I just want to make sure that I do to the right. And there's that setup that we recognize, right? We've got this really nice setup with, okay, inverse sine of radical 2 over 2. And we knew that if we were given a ratio, that what we're going to get back is an angle. And now we just have a really nice equation that sets that up. And yay, pi over 4 is a perfect answer there in the first quadrant for me to make that work, right? Now, I don't know that this stuff in between for unit circle values is really all that necessary, right? I'm super happy with this version. I would much rather you work quickly and know your unit circle well enough to get yourself to a point where you can just write that down, okay? Well, what if it's not a unit circle ratio that they give us? What if, call this one number 3, and I'll come up here to have a little bit more space. What if they said something like, okay, the sine of theta is 3 over 5. Right? That's clearly not a unit circle ratio that I recognize. Right? It's not 1/2, it's not radical 2 over 2, it's not radical 3 over 2. But it is between 0 and 1, so that's good. It's a y value between 0 and 1, so it's on the circle somewhere. But where, right? What is that angle exactly that's going to get us there? Well, we've got an equation that has sine of theta. What should we do to both sides? What should we introduce to the left side and then, of course, to the right to kind of undo what's happening to theta?
Inverse of sine.
Absolutely. Let's take the inverse sine of the left-hand side, which is sine of theta, and then we'll take the inverse sine of the right-hand side, which is 3/5, right? And the sine and the inverse sine cancel each other out, and it doesn't even matter what order you put those in. Like if you had the inverse sine of something, you could take the sine of that, and the sines would all cancel. Well, inverse sine of 3/5. Here, let's look at it. Because I got a calculator. I should be able to figure out what I get by just typing that in. So let me present real quick so you can see my calculator. But you could break yours out too as well, and see what happens when you type in something like this right-hand side, the inverse sine of 3/5. So that's second sine, right? There's inverse sine of 3/5. And my mode, you can see I'm in degrees so that I can recognize where that number is. And I'll feel a lot better about the answer than rather some version of pi that I really don't know. But when I do press enter, look at the kind of answer we get. Okay, good, a first quadrant answer. So there is a solution to this. It's not that there's no solution or that it's, you know, it's got us a spot, right? 36.86989765, and I got a pretty good feeling that number is just going to keep going, right? That 7, 8 decimal spots already. I bet that's going to keep going. So, and there's not really a whole lot of pattern. I don't recognize any sort of, you know, it's not 36.333333 or 15151515 or anything like that. There's no pattern to that degree measure. And so I don't want to round if I don't have to. I would love to write the right answer. What do you think the best way to write the inverse sine of 3/5 if that's the kind of answer that we get in the calculator? We get this irrational degree measure, right? Some theta is the inverse sine of 3/5 and it's 36 point blah, blah, blah. What's the best way to write an irrational number like the square root of 2, like 3 square root of 7, like pi, if there's no nice decimal that we can use that's exactly right? What do you
leave it as inverse sine of 3/5.
Perfect, right? That's exactly right. Okay, but what does that tell me? Okay, what that does is it gives me an angle that I really don't know how big it is. But what it does tell me is where it came from. Okay, and this is what I want to try to focus on today, using the idea that if you are given a setup, right, that's not necessarily a nice unit circle degree or radian measure, doesn't mean we can't draw a picture of it in the first quadrant. Right? I can draw myself, you know, the first quadrant of that unit circle, and I can get myself to a point where the y value of some angle is exactly 3/5. Right? And I can draw myself to a spot, and what was it, like 36? So I'll go to about, you know, 36 degrees right there. So there's theta right there. This point right there has a y value of exactly 3/5. Okay, and yeah, it's not a nice unit circle spot, but it is a really nice spot on this circle, right? 0.6 is, you know, exactly that y value, and that can be really nice. Okay. Cool. So I can draw myself a nice picture of that. Well, what good does that do me? Well, it does you this good. What if the real question wasn't what's the angle, but maybe the real question is what's cosine of theta at that spot? Like, here's some ratio of some angle that doesn't exist at nice degree measurements, right? It's not a 30 or 45 or a 60, okay? But I don't really care about the angle. Maybe what I really care about is, okay, here's the y value, give me the x value at that exact same spot, okay? Well, here's what we can do, okay? And this is what we start to get into, okay? If this is that location, right? I know what the y value is right there. Really what I want to figure out is the x value that goes with it. Which means I can draw myself a really, really, really nice right triangle at that spot. Okay. And if that's the right triangle that I can draw, what I should be able to figure out, hopefully, is what that x value is right there. Okay. Well, how do we do that? Well, let me do something to help you out a little bit. I'm going to break this triangle out of the unit circle and focus on it in a slightly different way. Okay, so that's why I'm going to come over here. Okay, what I want to do is I want to take this triangle. So I'm still here in number 3. I'm going to break this triangle out. I don't care exactly if it's drawn to scale or not. That's okay. All I really want to make sure that I do is that when I draw this right triangle, I'm drawing a first quadrant version of that, where here's the origin right there in that bottom left-hand corner, and the right angle is right there. Because when we deal with right triangles compared to any other triangles, man, so many things happen that we really, really like, okay? And remember what we know about this angle right there. The only thing that was given to us is that the sine of that angle is 3/5. And sure, being in the unit circle is really nice, right? Because the radius is 1 and things work out nicely that way. But if you're not given a unit circle type ratio, maybe it's not beneficial to restrict yourself to be stuck inside a specific circle. Okay, maybe what we do is we look at a circle that's a whole lot bigger or a whole lot smaller, or maybe just a little bit bigger or a little bit smaller in a way that avoids us having to deal with fractions the whole way. Because if the x value is what we're looking for and the y value at that spot is 3/5, I got a pretty good feeling the x value at that spot is probably going to be some either rational or maybe even an irrational number. And finding that could be tricky algebraically, having to deal with fractions the whole way. So let's back our lives up a little bit to a simpler time. A time in geometry when we dealt with right triangle trig. Okay, 4.3. I'm going to walk off screen here for a second, but 4.3. I'm going back to my title here. 4.3 is all about right triangle trig. Okay. So I just gave our notes a title finally, right triangle trig. I just want to focus on right triangles, okay? Yeah, sure, it's you center it at the origin if you like, and think about it in the unit circle if you really want. But let's make our lives a little bit easier. And sure, yeah, I mean, the axes are here, right? There's the y-axis and there's the x, sure. But really all I care about is dealing with things that are nice and positive to start, okay? And if I know some things about right triangle trig, basic sine, cosine, and tangent kind of setups, we know something from geometry about what sine really means when it comes to dealing with the sides of a right triangle when you're given an angle. Same thing with cosine, same thing with tangent. When we start relating the sides back to the angle that they came from, okay? If this is my angle right there, the side across from the right angle is the hypotenuse of a right triangle, right? The side way across from the angle itself, that's going to be my opposite side. The side across, the side next to the angle that's not the hypotenuse is adjacent. And we've got the fact that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Hopefully this is all coming back to you. There's a really nice little acronym that we used to remember all of that. It's coming back. SOHCAHTOA, okay? Because if I've got SOHCAHTOA, if I've got a way to not worry so much about being stuck inside a circle, but just dealing with the triangle that we can draw inside that circle, what sine of theta being equal to 3/5 does for me is it gives me a chance to draw a triangle. Because now I know two of those sides. I know that sine opposite over hypotenuse, that the opposite of this, that length is 3. And this length, the hypotenuse, is 5, right? And so if that was what was given, and here's the question, right? Cosine of theta, what is that? Well, cosine is just adjacent over hypotenuse, and I already know what the hypotenuse is. It's already 5. The only thing that we need to figure out is that length right there, okay? And if we know two of the sides of a right triangle, we can figure out the third pretty simply. What is the relationship between all three sides of a, and here's how I'm not gonna write the words right triangle anymore, I'm just gonna draw one. What is that relationship between all three sides of a right triangle? Give me one formula, one equation that relates all three of those sides together. Do you remember?
A squared plus B squared equals C squared.
What's that called?
Pythagorean theorem.
Pythagoras was the man, okay? He was such a rebel and just so beyond his time. Now, so many things get accredited to him when it was really like him and like a large group of other people that kind of bought into what he was selling. And at the time, a lot of his ideas were really out there. I'll just give you a quick anecdote about him. He started a cult and got kicked out of Greece. I'll just tell you that, okay? The long list of what Pythagoras did is really, really interesting. His most famous one, of course, is a squared plus b squared equals c squared. The leg squared plus another leg squared is equal to the hypotenuse squared in any right triangle. And if I know two of these sides, I can solve for the third, right? I can say, okay, 3 squared plus, I'm gonna call it like adjacent squared. Who cares what I call it? Is equal to 5 squared. Okay, so 9 is equal to 25. Subtract 9 on both sides, you get 16. So this adjacent leg, whatever that is just the square root of 16. I don't need plus or minus because I'm in the first quadrant and we're just talking about lengths of sides. So just 4. And now I've got this incredible way of, if you give me one trig ratio, I can use SOHCAHTOA to draw a picture of the triangle that I'm in. And if I've got a really nice, like if they're really generous with the choices that they use for these two numbers, we might get really, really, really lucky. And the other number is also an integer. Okay, when the three sides of a right triangle are all integers, man, this stuff gets a whole lot easier. And they try to use those numbers when we do trig at this kind of level, like a, in a pre-college level kind of trig, right? And they actually named those kind of side lengths. The side lengths in a, here it is again, a right triangle that are integers only. Okay, are so nice to deal with, right? And they gave them a name, okay? They actually called them Pythagorean triples. Okay, because all three of them are all integers. And there are 4 really nice ones to know, okay? Here's the first one, 3, 4, 5. Okay, obviously the biggest one is gonna have to be your hypotenuse for this to work, right? 3, 4, 5 works because 3 squared plus 4 squared is equal to 5 squared. And what's really cool about this is you can like double this and it still works. Like 6, 8, 10, 36 plus 64 is 100. Or you could 30, 40, 50. 3,000, 4,000, 5,000. 3 over pi, 4 over pi, 5 over pi. No, those aren't integers, but they still work. All of the multiples of 3, 4, 5 are side lengths in a right triangle, right? Now, what are the angles that are created, right? 36.89, 679, whatever. Not necessarily nice, but the side lengths are, okay? So 3, 4, 5, and any multiple of that. Here comes another one. 5, 12, 13. You don't have to have these memorized, but I would keep them handy when doing questions like these, so you don't have to do the Pythagorean theorem over and over again. Right, 25 plus 144 is 169. And multiples of this, 50, 120, 130, all works, right? Multiplying by 4, 20, 48, 52. works. Crazy, crazy, okay? The other two ones that are really nice that are relatively small, 7, 24, 25 is a nice Pythagorean triple, and then 8, 15, 17. Okay. Those 4 Pythagorean triples are just really, really nice to have ready to go. Okay. And so when they give us a trig ratio and they ask us for another one, there's a pretty nice process to get that done. Okay. And I just wanted to do at least one more with you and kind of write that process down so you can see it. All right. So there I am, right, writing right triangle trig as the title for this section. 4.3 is all about right triangles. And it goes back to just your geometry stuff, right? SOHCAHTOA and Pythagorean theorem and stuff like that. We'll expand on it for sure. But let's try now. Number 4. I'm just making these up, but I want to do the same ones that I did last class. Okay, so what if number 4 asked, okay, cosine of theta. So they're going to give us the fact that cosine of theta is 12/13. Well, not a unit circle spot, so I know I'm not looking necessarily for a nice angle, and that's okay, because that's not the question. The question is, what's, not the angle, but what's tangent of the angle, okay? And so that's kind of my setup. Well, let me just ask you this. Even though they didn't really ask this question, if cosine of theta is 12/13, and we know that we're not going to get a nice angle measure for that spot necessarily, and you can check that by just kind of typing in what we need to in the calculator. What do you think the best way to write theta might be if cosine of theta is 12/13?
Inverse cosine of 12/13?
Yeah, nice, right? Because the way to solve this equation would be to take the inverse cosine of both sides if the cosines were to cancel. Great, so there's theta, right? Now the question, of course, isn't that, but I just figured I'd throw that at us just to make sure that hopefully that's starting to stick a little bit, that if cosine of theta is 12/13, then theta is just the inverse of that. If it was sine, then it'd be inverse sine. If it was tangent, then it'd be inverse tangent. Whatever it is, cool. But the question is, what's tangent theta? And so what I've got is a pretty good strategy on how to deal with questions that look like this, okay? So step 1, what I think would be a really good idea is to draw a first quadrant, so a Q1 kind of, let's just say a right triangle. And when I talk about a first quadrant right triangle, what I mean is drawing a right triangle has this orientation to it, right? Where your angle's in the bottom left, your right angle is in the bottom right. Okay, there's my picture, okay? And now what I should be able to do, given the fact that cosine was given, what I should be able to do is label two sides based on that nice SOHCAHTOA setup. Okay, and again, first quadrant focus only at this point, right? Okay, so cosine was given. Okay, so that's what I care about right there. That if 12/13 is what cosine is, then the length of the side adjacent to theta is 12. And the hypotenuse is 13. Rather than saying this length is 12/13 and this length is 1 and sticking myself in a unit circle, this just makes that a whole bunch easier, okay? Hopefully we're cool up to that point, just kind of refreshing some stuff from geometry so that we can use it. I promise more stuff coming. Okay, cool. Now, let's find that missing side. Step 3, find the missing side length. Okay, to do that, Pythagorean theorem, right? And if we're lucky, the choices for these sides that were given are 2 of the 3 members of a Pythagorean triple. Because if they are, then I don't actually have to do the work. do you recognize, can you look back at the list of Pythagorean triples that had a hypotenuse of 13 and a leg of 12? And if so, what's the length of the other leg?
5.
And I don't need to see any work for that if you know it. Okay, so I would know those 4 Pythagorean triples. It's just super, super nice. Cool. Now that we've got that missing side length, now I've got the whole triangle. And I can find any trig ratio I want. I can find sine, cosine, and tangent for sure. Right? And so let's do it. Step 4, answer the question. All right? Answer the question. Whatever now that they're asking us to do, answer the question. Now I can do it. Now I can say, hey, what do you want from me? Oh, you want tangent of theta? Cool, I can do that. Why? Because I know the ratio for tangent. So catoa is the length of the opposite side over the length of the adjacent. Okay. Now, they can ask this type of question one of 2 ways. Okay. They can ask this question in like these 2 parts, right? Where they give us a trig ratio, cosine of theta equals whatever, sine of theta equals whatever, tangent of theta equals whatever, and then ask us for another one. Or, so like 2 separate things, like this equation over here and then this equation over here. Or they can combine them together into one trig expression that has 2 ratios in it. And what I mean by that is to take what we know theta is, and they drop it right there. Okay? This question could have looked like this to start. Tangent of the inverse cosine of 12/13. All right? Because in here needs to go an angle, right? It's tangent of something or cosine of something or sine of something or whatever, right? In here, I know I'm supposed to be like, in goes an angle, out comes a ratio, right? Well, the angle that's given is some irrational, right? It comes from a triangle that doesn't necessarily land nicely on the unit circle somewhere. So what they can tell me about that angle is the triangle that it came from and which sides are supposed to go where. And by seeing the question written like this, what I can really just imagine is, okay, tangent of some angle, right? What is that angle? Oh, it's the inverse cosine of 12/3. Well, what does that mean? That means this. What was the first thing I did? I drew a first quadrant right triangle, and I labeled the 2 sides based on this. And just like we did with composition of functions, right? F of g of 3, we worked from the inside out, right? We did g of 3 first, and then use that to figure out f of whatever that was. Same thing here. We're going to use the inside first. Use that to build a visual that we can then complete by finding that missing side, and then use that same triangle to evaluate. Okay? I know there's the new stuff, right? That's the kind of question they're going to ask. They're probably going to ask this question like this, okay? Let's do one more. Let's do one more so you can see it in action, hopefully. My marker's starting to give up on me. Let me try this one. Okay. Okay, number 5. Something like the cosine of the inverse sine of 8/17. Okay, the cosine of the inverse sine of 8/17. Just trying to find some markers. Okay, so what I need to do is I can just follow this path, right? I want to draw myself a first quadrant right triangle, and it doesn't have to be to scale, who cares? I'm just going to draw the same shape every single time. But I want to use what's given, and I want to start with what's in there on the inside. Hopefully that green you can see a little bit. Let me know if you can't see anything. Oh, my laptop's dying. Okay, I want to start on the inside there and see what picture I can draw, what sides I can label based on that right there. Well, they gave me some angle, and the sine of that angle is 8/17. Well, sine is opposite over hypotenuse. And if this is my angle in here, right, there's theta right there, what I know is that the side opposite that is 8, and the hypotenuse for that right triangle is 17. And step 1 is done, right? Just by using what's given on the inside and knowing your basic SOHCAHTOA, okay? Is there a Pythagorean triple that has 8 as one of the legs and 17 as as the hypotenuse? And if so, what's the other leg?
15.
Perfect. And Pythagorean theorem would do that for you in case you needed it, so you don't have to have these memorized. But man, wasn't that just so much easier to just be able to write down 15? Cool. Step 2 done. Step 3 done. Find that missing side length. Now all I really have to do is answer the question, okay, what's cosine of that angle that I just drew? Well, cosine, adjacent over hypotenuse, 15 over 17. And I'm done. I'll take a picture of that so that we don't lose some things. I didn't take a picture of the first one. I will. I did first period though, or second period. I just want to take some pictures of stuff so I can post them for you, for those of us that like to see it written out and don't necessarily want to copy too much stuff down as we go. Okay, cool. So there's kind of one really, really big, nice first idea about dealing with these kind of ratios. Okay, awesome. Now that was only sine, cosine, and tangent. Like, what about the other ones, right? Well, we've got something for the other ones, don't worry. And I've got a really, I don't know, I like to think of it like this. A nice way to think about how the relationships just get flipped, right, when we're dealing with secant and cosecant and cotangent, stuff like that. Right, so SOHCAHTOA was the basic ones, right? That one is your 3 basic trig ratios for sine, cosine, and tangent. Well, they have their reciprocals, right? Okay, so the reciprocal of sine, sorry, I'm probably in the way. The reciprocal of sine is cosecant. The reciprocal of cosine is secant. The reciprocal of tangent is cotangent. So there are my 3 kind of starting letters for each of my triplets there. And all I'm supposed to do with reciprocals are put them upside down, which means all I have to do with these last 2 letters is switch their spots. O and H become HO. AH becomes HA, and OA becomes AO. And yeah, you know SOHCAHTOA, but have you met, this is just the best, man, CHO-SHA-COW. CHO-SHA-COW. There are my reciprocals. SOHCAHTOA and CHO-SHA-COW. I just cannot say that enough. It just makes me smile. CHO-SHA-COW. Okay? And we'll use that. We'll definitely use that, because I could have asked you for the tangent of the inverse secant of 5/3. And we could figure out what angle we came from by drawing a triangle that has that kind of secant to it, and go from there. Okay, super cool stuff. And so that works, right, no matter what space you're in. And we can break this out of the first quadrant too. We could do second quadrant, third quadrant, fourth quadrant stuff. We'd have to deal with some negative measurements, right? Because we're in a quadrant that maybe has a negative x value. And I know we're measuring lengths of triangle size, and those can't really be negative. But if we put them on a graph somewhere, they certainly can. So, but focus on first quadrant stuff for now. We'll expand on that in case I think we have to. Okay, cool. All right, last thing. Ooh, we made good time today. Usually I'm super slow. We're doing well today. Okay. Hopefully that was okay. Okay, that's your basic right triangle trig stuff. SOHCAHTOA, CHOSHA-CAL, and being able to draw right triangles and find missing sides and find irrational angle measures and be okay with writing them as inverse sine of 2/3 or inverse cosine of 1/17 or whatever it is, right? Because they just don't give us nice degree or radian measures. Cool. All right, last thing that I wanted to do, and again, we're not going to play with this too much. I just wanted to have you have it. I just want to give it to you now so that when we come back, we'll be able to use it in a little bit more interesting kind of ways. Okay. What we are starting to do with this stuff here by combining different trig ratios into one problem, right? Sine of inverse cosine of something. We've got these expressions, these equations that have more than one trig ratio, trig function together, right? And we can relate them in a lot of really interesting ways. I mean, the list is just endless of the ways that we can, like, in one equation, have more than one trig ratio, and it always be true. Like, there's ways to relate them in a way that what's true about it in a unit circle is true about it in circles that are smaller or bigger. Doesn't matter where we are. We have a truth. We have things that we can rely on, that we can count on, and we don't just have sine by itself or cosine by itself. We can relate them to one another. Okay, and that's what I want to get into today. I want to start talking about relationships between multiple trig functions, trig ratios, that are always true. Okay, so this exists kind of on its own up here. Relationships between BTWN, multiple trig ratios, functions, whatever you want to call them. I'm going to call them functions, I guess. That are always true. Okay, and this is right triangles, this is isosceles right triangles, this is obtuse triangles and scaling triangles, and in a unit circle, out of the unit circle, trig stuff that's always going to be true. Okay, and we give that its own name. We call them trigonometric or just trig identities. Okay, things that are always going to be true that you can count on, guaranteed, no matter what. Okay, and there are a ton of them. Okay, but they all kind of start with some basic ones. Okay, the first ones you already know, that sine and cosecant are reciprocals. That's cosine and secant are reciprocals. The tangent and cotangent are reciprocals. Those are called the reciprocal identities. That no matter what, no matter where you are, that's always going to be true. Okay? There are some other ones as well. The first ones I want to talk to you about are the quotient identities. Okay? And there are just two of them. Okay? And here's where they come from. Okay, now when I talk about quotients, I'm thinking about the trig ratios that have both like x and y in them. And the only ones that have that are tangents and cotangent. Okay, but I don't want to put y and x. We already know that. I want to relate it back to another trig function. Well, quotient. So we're talking fractions here, and of course, I mean it's tangent, so it's going to be y over x. But what's another way that we can write the y value at a certain angle and just not use the letter y? Is there a trig ratio, a trig function, that means the y value of a certain point moving along a circle?
F of x.
Sine?
Sorry, say that again at the same time. Which trig ratio means y? Like the y value of a point along the unit circle?
Sine?
Sine, yeah. And remember, tangent is just y over x, right? And so I can replace y with sine of theta. And it doesn't matter where I am, that's always going to work. Well, sine is y, what's x?
Cosine.
Nice. Tangent of theta is sine of theta over cosine of theta. Every time. No matter where you are, no matter what angle you're looking at, no matter how big the circle it is that you are drawing, whatever kind of triangle you're dealing with, tangent of theta is sine over cosine. Okay? And cotangent is just a reciprocal of that, cosine of theta over sine of theta. Exactly. And for the very first time, we now have a way to relate not just 2 trig ratios, but 3 of them all together. That tangent is the ratio of sine over cosine, cotangent is the reciprocal of that. Okay, cool. So that's a big, big, big one that we are definitely going to use plenty. Tangent is sine over cosine. Okay, cool. One last list of ratios. And since we got ourselves in kind of a Pythagorean kind of mood, and man, I could talk about that guy forever, let's talk about some Pythagorean identities, and then we'll be done. I think that should do it. Okay, now remember where this stuff comes from. All of this was based on an understanding that we are potentially, right, it all kind of started in the unit circle with a radius of 1. And that if I opened up some angle, that point right there, xy, could be written as cosine of theta, sine of theta. But what that really came down to is the fact that I could draw a right triangle whose x length is cosine, whose y length is sine, and whose hypotenuse is 1. And if we can do that, if I can draw a right triangle and I know all 3 sides, I can come up with an equation that relates all 3 of those sides together. Where I take one of the legs, square it, another leg, square it, add them together, and set it equal to the hypotenuse squared. I can do sine squared plus cosine squared, and it's equal to 1 squared. Now, how should I write that down? Well, so don't write this yet. I just want you to look, okay? If I write sine of theta, and I want to take that whole thing and square it, so parentheses around the whole thing and square it, that's pretty cumbersome and a little sloppy, and there's just a lot going on there for something as simple as just like sine squared. I mean, it's 2 syllables. I shouldn't have to write so many things down to do that. So, well, like what if I drop these outside parentheses, right? Doesn't that kind of look like the angle itself is being squared? I don't want to square the angle. Like I'm stuck in this triangle. I just want to take the sine, the y value, and I want to square that instead. But this is just a little ambiguous, right? I can't really quite tell what's being squared. And so the conventional way that we are going to write exponents or trig functions is not at the end, okay? We're actually going to put them in between the trig function name itself and the angle so that we know we're squaring sine, not squaring the angle, okay? So there it is, sine squared plus cosine squared, and I still read it out loud like that. I'm just gonna put the 2 in between, okay? Sine, and you can say sine squared theta plus cosine squared theta. Well, that's equal to a hypotenuse squared. Well, 1 squared is just, and no matter what, pick an angle, any angle you want. Sine squared plus cosine squared is equal to 1. Guaranteed. Okay. Now that's only 2 of them. What about cosecant, tangent, and cotangent, and all that? I can just mess with this equation. I know we're a little past 11:15. I just got one last little quick thing to do. I'm just going to kind of come over here to show you my work. Okay. Sine squared theta plus cosine squared theta equals 1. Okay, if I want to take an equation and mess with it, as long as I do something to the left and do it to the right, we're good. As long as I'm not dividing by 0, we're okay. And so what I'm going to do here in this identity that is guaranteed to be true because it just came from a right triangle, I'm going to divide by the same thing everywhere. I'm just going to make sure it's not 0. Okay, I'm going to choose what to divide by. And I want to divide by one of these, either the sine squared or the cosine squared. Doesn't matter. I'm just going to pick one of them. I'm going to start by dividing everywhere by sine squared to develop another Pythagorean identity that just relates different trig ratios. Because watch this, look, something divided by itself. Oh, okay, well, that's 1. Nice. Cosine squared over sine squared. Okay, well, let's back up a little bit. Just regular cosine over regular sine is cotangent, right? We figured that out, right? That was a really nice quotient identity. Well, if cosine over sine is cotangent, what do you think we should call cosine squared over sine squared? If cotangent is cosine over sine, what do you think cosine squared over sine squared would be nice to write?
Cotangent squared.
Awesome. 1 over sine squared. Well, regular 1 over sine is cosecant. So 1 over sine squared, cosecant squared. Guaranteed every single time. Crazy. So cool. Okay. One more, all I have to do is divide by cosine instead of dividing by sine. And of course, I'm talking squared. And I'm just developing additional identities by just manipulating something that I know is true. Doing the same thing. Add 3 to all sides, everything's still true. Multiply by 7, all good. Divide by cosine squared. Okay. Sine squared over cosine squared. Well, tangent is regular sine over regular cosine. This is sine squared over cosine squared. So this is tangent squared. Plus cosine over cosine, 1, equals 1 over cosine secant. Well, it's 1 over cosine squared, so secant squared. And there are your 3 Pythagorean identities. Boom. Done. First semester of math. Done. Okay, what I'm going to do is I'm going to send something out today, tonight, maybe tomorrow. That will be optional. That just helps you practice the things that we've done so far in trig. A little extra credit for those of you that want that last little push in case you are like really close, really close to that grading scale that I know that they've adjusted, right? And 88 is now an A, 76 is a B, 64 is a C, 52 is pass, or to kind of help you guys out. So none of us are down towards the 52s, but some of us might want that little extra boost. So keep an eye on that on Canvas. Nominate somebody for the Apple Award if you're interested, but nothing you need to do mandatory. There's no extra work for the rest of the semester. A little optional stuff if you want a little extra credit. I will just take attendance on our final day, right, so that I can take attendance. So I'll send out a link for you to just either do that remotely or you can just stop by office hours. I'll just be sitting on my computer grading. But we took our final already. We're good. So grades are basically set where they are. And we're done. You can focus on other classes as you get ready for next week. Really happy with how things went for semester despite all of the craziness that's been going on, and really impressed with how hard you guys have been working and how often you show up to these and engaging with me and humoring me while I enjoy all of this crazy stuff in an empty room. It's so sad, but I miss you guys and wish you the best next week. Study hard. Good things happen to those that work for them. Let me know if I can do anything for you to help out. Have a great winter break. Well-deserved couple weeks off. Stay safe. Have fun as much as you can while keeping yourself, your family, and people you care about safe and sound as we power through this. Expect that when we return to January, it's going to look just like this. I don't think anything's going to change to start, but hopefully, numbers start to die down a little bit, and we can get ourselves back to at least hybrid, and we can get back to school. So But good luck next week. I will see you just briefly if you'd like to stop by during office hours on what is that, Tuesday from I think 10 to 11:30 is when our final schedule, but we've already taken off, so we're good to go. Nothing you have to do from there, but stop by and say hello. Okay. So thank you. Can't say it enough. Have a great break. Nominate somebody for the Apple Awards if you're feeling it, and good luck on finals next week.
Thank you.
Thank you.
Thank you.
Thanks for everything.
Thanks, Rosie.
Thanks.
So much.
You're welcome.